Now, one important thing to understand, you can evaluate the integral over c of m dx plus n dy plus p dz, which is just our integral of f dot t ds around the curve, by evaluating the integral over the surface of curl f dot n times the surface area increment. And you can do that for any surface bounded by C. That is, S can be any surface that has the boundary of this curve. So if you have a curve that bounds, let's say, a segment of a sphere, you don't have to integrate this over the spherical region. This is going to be true for any surface bounded by the curve C, and that would include the plane region. If you take a plane slice of a sphere, you have a plane region around that curve, as well as the curved region. It's generally easier to integrate this over the plane region because if you're in a plane, the normal vector is constant. And you saw that before, even though there was some potential confusion because of the expressions we were integrating, there wasn't really much of a complication with the constant normal vector. It would have been much worse if the normal vector had been a variable. Okay? So if C lies in a plane and then the normal vector is constant, and plane regions are often a lot easier to parameterize in any case. So there are a couple of reasons that if your curve C lies in a plane, then you should try to parameterize the surface within that plane. Okay, or you should try to integrate over the plane region that's bounded by the surface rather than some curved region. If C is the intersection of a plane with another surface, then C lies in a plane, and C previous. If we cut a paraboloid with a plane, cut a sphere with a plane, cut anything with a plane, then C is going to be a plane curve, and the region bounded by C can be the region of the plane that lies within that curve. Again, that's going to make things easier. Okay, in all cases, your vector function f is mi plus nj plus pk. So that if you have this form of the integral, if you don't know what the function f is, you can easily read it from the integral. It's just whatever the coefficient of dx is times I plus the coefficient of dy times j plus the coefficient of dz times k. So that it's going to be easy to evaluate the curl of f. So if we're given this form, we look for this. We hope for a plane region. But whether we have a plane region or not, the curl of f is going to be easy to calculate, provided we can take the derivatives of the m, n, and p functions.